week 13b, we're going to do the following. Okay? Then we want to do a look back, okay? To see our journey to today and where we are at. So I'm going to go back by looking into Robust Control Toolbox, okay? Robust Control Toolbox, okay? And then we localize where we are. So we are here. Where we are at. Okay? To understand that. The second is we're going to continue to discuss why gap metric. Okay, why? What kind of benefit we can get if we look into the gap metric? What kind of benefit we get? I'm going to check IEEE Explore to check out what's popular, okay? My point of view is gap metric in this big data area that will offer insights, let's say additional insights, okay, into the robustness issue. So far, our robustness point of view is from Cummins' book. I think this modern control is already, to me, is already classical. And this textbook is already 20 years old, okay? Okay? So, then we need to ask, what's beyond this? So then, what's next? Okay, what's next? And I have to tell you that in many universities, they never cover gap metric part. Because this part is very difficult to grasp those concepts. However, it's useful. I'm going to convince you that it's useful. And that is effective. So you invest time to learn more. And for these 2 lectures, there's a corresponding book I uploaded by Minicons. So the reason is everybody feels, wow, that makes sense, but everybody's not using it extensively because it's a little bit hard to get into this. So if you want to do good research, I suggest you look into gap metric. Okay, gap metric is a more general framework. So that is what I'm going to do today. Then in the week 14, I'm going to do Pontryagin maximum principle based optimal control problem solution. And I'm going to explain what is the algorithm between the rails. And I'll explain to you, we have a project design for this one, okay? Project design for this one. Or lab, okay? And then week 15, so week 15. So we probably will go to fractional order system and focusing on fractional order optimal control problems or fractional order variational calculus. Okay, variational calculus of FOCV, calculus of variation. Okay, FOCV, and its corresponding fractional order Euler-Lagrangian equations. Okay. About solving, towards solving the optimal control problems. So that's the mini plan, okay? From topic point of view, okay? From topic point of view. So first of all, I want to go through this one with you. Let me do this. They should go down. Good. That one, can you close that one? Okay, so you focus on the screen, okay? Don't on me. I'm going to use my mouse. Did you see I have a huge mouse? Okay, you see it? No, go down, this blinds. Interesting.
I guess those are manual.
Yeah.
Those are manual.
Oh, okay. Can you do it? Yes. See, automatic control. Yeah, may not always work. Okay, please block it. And also this one. This one. Oh, only for this. Yeah, makes sense. Okay, so this is better. Can you guys see my screen? Okay, so I want to show you that this is a 2019B, okay? 2019B. So every year they release two versions, A and B. And this is, the last maybe 10 years they do this way. I'm the latest one on that. So if you want to check what's inside here, you can type VER to see what you have in here. So you can see, if I go from here, so that is we paid for the site license. Okay, I pay $500 to install for everybody's computer in my lab. Okay, for students you can also just put in. So you can see this aerospace, bioinformatics, communication, computer vision, control system, code fitting, DSP, data acquisition, deep learning toolbox, econometrics toolbox, embedded coder toolbox, financial toolbox, physiologic toolbox, GPU coder, global optimization toolbox, image acquisition toolbox, instrumentation, and compiler, report generator. This is also interesting. Mapping toolbox, navigation, optimization, parallel computing, PDE, ROS toolbox. Can you see? ROS stands for Robotics Operational System. Reinforcement Learning Toolbox. Can you see that? Robotics Toolbox, Robust Control Toolbox. So we are learning this course. We have a supporting toolbox. It's called Robust Control Toolbox. I have experienced the different version of this robust control. And actually they divide the robust control in many small pieces like RMI, linear matrix inequality toolbox, parameter toolbox, interval toolbox. There are many like QFT toolbox, quantitative feedback theory toolbox, and of course you have a mu synthesis toolbox using mu. So I'm glad to see that finally we converged to one single toolbox while keeping all the previous like RMI, mu synthesis as called older version, okay, older version. So that is toolbox, okay. So there are two things parallel. You have MATLAB, you have Simulink, okay. In MATLAB, it's called toolbox. In Simulink, it's called what? It's called block set. Block set. You have block set, okay? So in fact, all these things are considered as a Simulink-based block sets, okay? So machine learning, statistics, symbolic math, system ID, okay? So I think each toolbox should correspond to a course semester long at least, right? So we should have a system ID toolbox, a course dedicated for like how to get GFS, how to get a model from data, and how to estimate the error bound of the model. Okay, so those are very important skills, right? For example, I just give you a simple task. Can you do me, I give you a step response. Can you give me a transfer function to fit it? That kind of work you should know, okay? And so on and so forth. Text analytics to analyze the text and the wavelet toolbox, okay? It's like multi-scale model data analysis. So for then if I do this, if I do demo, okay, just type demo, okay? So you are going to see you have a lot of things in here. So these are all the toolboxes we just have seen easily, right? So you only need to focus on this. So if you have an idea, if you don't have an idea about how the toolbox is working, is for what purpose, you simply click like image processing toolbox. They will have a lot of things in here, right? So you can go through all these demos. But today, we only look at this one called Robust Control Toolbox, okay? The reason I want to show you Robust Control Toolbox, so I show you Robust Control Toolbox, okay? So I only want you to know how they organize things together. And then you understand, in your knowledge about robust control, what are the essential parts. So there are 4 parts, okay? Can you see that? First part is robust control basic idea, okay? Basic idea, the overview, okay? Actually, it's only 3 parts, okay? 4 parts, sorry, 4 parts. So the first part is how to describe your uncertainty, how to model your uncertainty, how to quantify your uncertainty. So that is this one. There are 6 examples there, okay? 6 examples. Then after that, we want to understand how the uncertainty will affect our stability and performance, okay? So that's analysis part. Remember the thing called MAD, we started with M. This is M, right? This is A. Then what's that? This is D, okay? Modeling, analysis, design, the MAD principle. But there's another thing is called implementation, right? You did modeling, you did analysis, you did design, then you did implement, right? When you implement, then you will face the issue of your order of your controller might be too big. It's a big, high order control. So really need to talk about simplification. And similarly, when you get a nominal model, you also need to talk about model simplification. So you don't really have to work on very high order of the model. You just use a reduced model, and those approximated part, you could have very accurate estimate of the bound. Remember Hankel norm, okay? Remote minimum realization, Hankel norm based model reduction. Just the Hankel norm, you just rank them and you cut all the tail. And this, the part you cut off, how big the uncertainty you introduced, the norm, is precisely can be computed. Okay? That's we covered in the class. Okay? So this part, we have 4 examples. But I think in here we have talked a lot. So I'm going to do one by one with you. Okay, I'm skipping the getting started, the warming up. You can see getting started, you have some specific examples to show you modeling, analysis, and design to give you a feeling, okay? To give you a feeling. Robust control. You basically work with what? You work with a family of plants, okay? Then you design a controller to robustly control it with satisfactory performance and stability requirements. So that is getting started. You have 3. The 3 thing is called M. See, M, A, and D. Okay, M, A, and D. And when you have this design controller, the controller may be high order. This one also maybe the model is high order. So there is a dedicated part talking about model simplification or model reduction, okay? So, the uncertainty system representation. I want to add a remark why I'm doing this. So, you can see that when you read Kaminzo's book, it's like 500-600 pages, this thick, okay? There's tons of stuff in there. And you get lost into this forest sometimes, and you see all the trees, different types. And I want you to get out and look at this. What we have learned is just MAD, okay? Facing with a family of models, okay? A family of system models. So the family of system models, then first step is to do uncertain system representation, okay? So how you build and manipulate the uncertain models. And so then giving an uncertain system, you suddenly get a cluster of all these responses, okay? And then this is a time, this is a frequency, okay? Time and frequency. And also how you can handle uncertain models in simulink. This is also quite interesting. You can see they also have a family of this. Because you have a set of models, then you have a cluster of the outputs like that. So instead of as one step response, you have many step responses. Okay, so you have uncertainty models, you have uncertainty models in simulink. Okay, so these all can be done. So I go from here. So then, after you had this model, you put it into uncertainty format, and what you are going to have is to do is a stability analysis. Analysis, we have two cases. One is performance, one is stability. So we call RP program is a robust performance program, and RS program, robust stability program. Of course, we already assume you know how to do nominal stability and nominal performance, okay? So, and here you can see the mu showing up, the mu analysis, And I think we covered about structured and unstructured. So we talked about unstructured uncertainties first. So then based on a simple small gain theorem, right? Small gain theorem. If the gain less than 1, there's no way you will be unstable. So then we introduce the structure. Okay. Then we talk about mu. Mu, you should understand there are 3 letters behind it. It's called SSV. What's that? Structured singular value. SSV. Okay. SSV. So it will lead you to a less conservative robustness analysis. So these are the examples for DC. Worst case, you have a lab to analyze this, okay? And you have a first lab is to do you know, depending on the card, let you to appreciate the water bed problem and body's integral, okay? Sensitivity. So those things were not highlighted enough in your previous entry-level control course. Okay. Lab 2 is on analysis, okay? 3 is on design, okay? So these are just coding the codes, you get the results, okay? But now I feel like they already did this one for you. So for example, if you want to do mu analysis, you open a live script, then you go through that as if you have run it through, but they just list everything for you. Let me do this for you. So they give you examples, then you run through, okay? You don't have to run, in fact, okay? You don't have to run. So basically, as if you are running, it's like mu analysis, They tell you, oh, you create uncertainty doing this. So you basically you can run this, but you don't have to. Just say, oh, these are the codes. Then they explain to you. Then they just explain to you, explain to you, explain to you. And they have the figures for you. So MATLAB is evolved much nicer. Okay, much nicer. So robustness analysis, okay, robustness analysis, mu analysis, and how to do it within the Simulink, okay, stability margin there, how to compute. There's one part we never actually talked about, Monte Carlo, okay, Monte Carlo. So Monte Carlo is try to enumerate the members from the family of the plants. Then we check everything, then we can see envelope, and to see up and lower bound, okay? So you do sampling from that family, okay? Sampling, all uniformly pick up. Family members, then run, then get a response, okay? And the Simulink model, yeah, we have Simulink model as well. And you can consider Simulink, some non-linear models into here. So then you linearize it and consider others as uncertainty. So let me just to wrap up here. For the analysis part, we basically have mu as a tool, and robust stability, robust performance, and mu. So that's illustration we have learned in the different chapters. So analysis part. The design part, okay, is design part. Robust controller part is the design part. We talked about H-infinity synthesis. It is, there are 3 examples in there. We already talked about mu synthesis, like decay iteration. And again, the warning is theoretically giving the structure of the uncertainty. You may not have the mu synthesis controller exist. Okay, it may not exist. It may not exist. There's no guarantee. But usually you will get a working controller. Usually, I'm saying. Mathematically, you can always have a counterexample in there. So this one, let's see what's have. So for H-infinity structure is something we covered. Okay, we covered. How to do H-infinity without uncertainty structure? It's already covered in Cummins' book. Okay, but with structures was not covered in his book. I believe new versions of robust control should include this part. Okay, when the uncertainties, you know it has some structure, then how you can do your H-infinity design. Okay. Okay. So usually we call this as fixed structure. A fixed structure. Okay, meaning your controller could be say, oh, we don't use your high order H-infinity controller using unstructured uncertainties. So we assume that we have the fixed structure. Like I insist that I use PID. Okay. Can you synthesize using H-infinity as my objective function, then optimize my parameter, have a systematic way to achieve it? The answer is yes. Yes. So this, you can open this one, you can run some examples in here. That's one thing. Live active suspension for this robustness study.
Dr. Chen,
yeah.
so it means that somehow it's possible to synthesize an H-infinity controller to find with a PID controller structure?
Yes, yes. People say H-infinity optimal PID synthesis or design. Yes. So that's the point. for traditional H infinity control, people will get a wrong impression that the controller has to be very high order. So the order should be the 3n. Like if you have a internal state realization, the state is n, then your observer will also be n. So it's like 2n. But what if you have a weighting filter, W? You weight, okay? That realization, you add another. So it at least 2n plus maybe 2n, output is q, that 2q, okay? Sometimes you have input, number of inputs, number of outputs, okay? So 2 times number of states, that's for observer, okay? And also you need number of outputs, you need the filter, W-O, and input, W-I. So those filters, so number of inputs, number of outputs, these numbers add together at 2n. That's your controller's, full controller's order. It's very big order, okay? Very big order. Okay, so, yeah, so robust control of active suspension. And remember why we need to care about this. Do you happen to know? And your car has a suspension, right? Suppose you have an active suspension, meaning you have a control like MR damper. MR stands for magneto-rheological material. Fluid, okay, MR damper. So that one, so you add different voltage, then the damping coefficient is different, okay? So that is called active suspension. So the robustness means you better to have a very consistent comfort feeling. So you drive a car, you have 4 passengers in the car versus 0 passengers in the car. The comfort level is so different. You don't want that car, right? So I have a Prius. I don't like it. Do you know why? The suspension is very bad. The Prius suspension is very bad, and you have 2 people, you have 1 people, and 3 and 4. You will feel differently when you drive. So you will feel very, very different. You even feel it. So, but for my I have another minivan. It's called Sienna. Okay, that's different. It's very different. So it's more robust to number of passengers, right? So the robustness is very useful. So that's for H infinity synthesis. We already have the commands to do that. Again, we have mu synthesis. We have several examples here. We can do the decay iteration and introducing the mu and with structured uncertainties, okay, SSB. And it's based on so-called decay iteration. So you can see the decay iteration here, okay? But other people introduce some other things like mixed mu synthesis. I don't need to worry about this. These are different types of filtering, okay? You put emphasis on something. Then just mix it then. Or you suggest you have multiple objectives and you put them together, okay? Like, oh, I wanted the arrow to be small, I wanted my energy also to be small, okay? That kind of thing, you mix them together. So this is, let me go back and to see the big picture. So we are here, part 1, M, part B is A, part C is D, design, M-A-D, okay? So we are looking at the D part, and we talk about H infinity, we talk about mu, and we talk about loop shaping synthesis. Okay, loop shaping synthesis basically, I feel like loop shaping idea is you use sigma bar and sigma underbar to make sure that your system to be controlled is shaped, okay, or shampooed, okay, no, probably conditioner, okay, to such a way that the gain in the high frequency is low, and the low frequency is high, okay, that's a simple principle. But your original system to be controlled may not be in this way, okay, but this is the status you want to achieve. How to do that? Add waiting filter, okay, W, then so that you can make it happen. Then you, based on this conditional system, you design your H infinity controller. Think about your order, okay? You triple your order, okay? And then you put W1, W2, and combine with the controller, then becoming an actual design controller for the original plant. So this process is also called Glover, case Glover, okay? Glover McFarlane procedure, okay? There is a loop shaping toolbox. But on the other hand, we don't need that. This is already built in the robust control toolbox. So this toolbox is already very complete. So the previous old small toolboxes will not obsolete. So will not be used like mu synthesis toolbox, like RMI toolbox. You don't need it. It's already built in. Talking about MRI, I suddenly recall one thing. Remember when I introduced you about structured H infinity control synthesis, there's a criticism about RMI. There is a hidden, I forgot to highlight that. RMI is always doing outer approximation, okay? It's inherently conservative, okay? Inherently conservative. So it is only providing sufficient, sufficient condition, but it's not necessary, possible. So, while this procedure invented by the scholar who proposing this structured uncertainty-based H infinity synthesis, they suggest something from inner, okay? It's called inner approximation, okay? So loop shaping, I believe this is not very hard, okay? So then there's a high mat. It's called high maneuvering control design. It's a real world problem. It was a real world problem. Okay. I hope you enjoy playing that lab 3, right? Lab 3. Okay. Lab 3. So yeah. Then if you want to consult back, you can run these demos. Okay. So we have 3 demos. So after that, there's something called robust controller tuning. Okay, tuning. So these are other types of robustness, other types of robust control problems. Say for example, I usually say that, oh, you have uncertain set. There are infinite number of plants in there, you want to control them. But what if I say, I only have 2 plants, okay? I want you to design one controller to simultaneously control both of them. And stability and performance are best compromised, best trade-off, okay? Not compromise, trade-off. So that's already in the literature. It's called simultaneous stabilization. Okay, how to design a controller to achieve that. So that can be reformulated into robust control problem using this toolbox. Okay. So another thing is, say for example, you have a given plan, but the parameters are uncertain. Previously, we say, oh, the parameters is from a it's interval. Okay, there's infinite possibilities. But in many applications, they say, oh, the parameter is not sure, but it could be from a finite set. So that's why it's a multiple values of parameters, okay? So multiple means you can count it, okay? So this is a simultaneous stabilization problem, right? Okay. Then fault tolerant can be also formulated as a robust control problem, okay? So basically you have multiple modes of the plant. If this is bad, then the system becomes P1 becomes P2. If this component is bad, then the whole system becomes P3. So I have certain faults and then corresponding certain plants, discrete number of plants. So I want to design a controller to tolerate those faults. That basically says what? Simultaneous stabilization. So this, to me, is similar to that. Is that right? Mm-hmm. Something like that. Of course, this one's only said parameters. This one may say, oh, my system order could be also different, okay? Because of the components is bad. So they also do worst case control. The worst case scenario. It's called robustness tuning. Okay, robust tuning. So you want the system to be robust. You really need to ask. Whenever people use the word robust, you need to ask the following question: robustness with respect to what? Okay. Again, we return back to M, A, and D. Modeling, analysis, and design. So without modeling the source of uncertainty, we're talking very bad. So again, I want to finish my part 1 of today's lecture about H-infinity synthesis. So this is just robust controllers coming back with robust toolbox. So you can see 1, 2, 3, 4 parts. Okay, 4 parts. So where we are, let me point you to here. We are in the M, A, and D. We are in the D part. In the D part, we are actually talking about loop shaping synthesis. Okay, but we haven't been there yet. We simply try to introduce a new metric or new ruler to measure, or new metric, new index. Okay. You have H2, you have H infinity, you have what? Mu, okay? So to serve as a metric, to measure how good, how bad the performance is, okay? Or the stability margin is. But this time, we're going to introduce something called gap metric. Okay, gap metric. I already showed you last lecture that gap metric H infinity norm can be very small, but the gap can be very big. Make sense? I think that is a very interesting justification of using gap metric. Now, today we are going to introduce Minicons mu gap metric. Okay, let me see. So we have seen an example like this, right? Have we? Yes. So we have seen this example here. So these two, what's the distance between the two? The H infinity norm is infinity, okay, in the open loop. But in closed loop setting, so the distance is actually very small. Okay, it's very small after you close the loop. So we really need to understand the closed loop. Okay, and I hope this can be consistent with the open loop distance. So beta, this one and this one kind of telling the similar story. Okay, that would be nice. Okay. So we need a new measure or new metric or new ruler, okay, or new index, name it. And in this part, we're heavily using normalized coprime factorization. Okay, you had a sense how to do that. So because if you say, oh, this is a numerator, this is a denominator, it's difficult to discuss how you deal with S. To me, S is very, very problematic. You know, it's not. It's a differentiator. It's difficult to handle. So you better to do a numerator is RH infinity member, and this RH infinity member. So it's a coprime factorization. Each factor is in the RH infinity space. Okay. So with that, we're going to see. Actually, the definition is here. So we do a left stable coprime factorization and normalized. Okay. So you see, we have two things here. The one is a tiered on top. Okay, that's called what? So this is right. This is left. So this is actually left coprime factors. And you put the tiered in here, this guy is anti-stable, meaning you replace S inside N of S here by minus S. It's called anti-stable part. If you have a stable and anti-stable part multiplied together, what are you going to get? Something called zero phase. Zero phase. You think about here, this is 1 over 1 plus S, okay? So S is j omega, okay? Okay. Then you have a 1 over 1 minus j omega. Then what are you going to get? You get a real part. Yes. There's no imaginary part at all. That's called a zero phase. You don't have a phase. So this one has no phase. You understand? I thought you know, but I better to point out to you. So there isn't any phase in here. It's not complex anymore. It is all real. Okay? So stable, unstable, then you multiply together, it becomes zero phase. Okay? You have zero phase. Yeah. So it's basically like conjugate. Okay? You have a complex number and conjugate number. Then you multiply, you become a real. So we have seen examples how to do this normalization, but doing this is needs some training, and most of you guys, including myself, when I was educated in control, I seldomly used this form in my research. But now, for gap metric, it shows this probably is the best starting point. Okay, because they usually use the coprime factorization to define the gap, okay, between the two systems. So from computational point of view, okay, so basically your P1 and P2, so in fact, it's like you have a free tuning knob in here, Q. So M2, N2, N1, N1, so these are all the right coprime factors, okay? Then this is RH, this is H infinity means a stable, proper, not necessarily stable though, it's proper. H infinity, the norm is finite. This is a filter, okay? And you search all the filters, you check the smallest one, smallest H infinity between here and here. So that is called the distance between P1 and P2. And this is not a vector though, this is just directional, okay? From P1 to P2. Because if you put Q in here, it will be different, okay? It will be different. So then you see you switch, you have another one, then you pick up the maximum one. Is defined as a gap between P1 and P2. So don't get me wrong and don't get me complicated here. It's simply you agree that you start with co-prime factors here and here, and you define a directed gap, and then using the maximum you get you get the gap between two systems. And it turns out that this is a magical metric, okay? Very useful, give people good insights, okay? And you don't have to worry too much. You just gap metric, you just do that, okay? Just do that. So the gap metric is 0.09. So let me go back to this slide. So we are having closed loop system like that. So this is the distance, is like difference between the closed loop is close according to each infinity. But this one is not. So for our gap metric, these two will be similar. Okay, will be similar. It's not like too extreme, okay? So that's why gap metric makes better sense in this scenario, okay? In other words, H infinity may not always be good in terms of measuring the difference between the two members. Of course, H infinity norm is useful in terms of worst case scenario, okay? Max, 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 okay? Max of max, okay? Of course, that's useful, but in this case, it fails. The H infinity norm fails. Okay? While gap metric succeeds. Okay? Succeeds. So you can see the open loop distance is also small. This open loop distance is also small. Okay? And the closed loop system distance is small. So that makes better sense. And we have this command. So I get you a gap. So there are some ideas. Can you see it? So you want to understand. I don't know what is the command name for gap metric. Okay. So you really want to see what's in the MATLAB. You should do this. Okay? This is a trick not all of you know. Okay. It's called look for. Okay. It's like Google. Okay. Look for gap. Okay. Then they will find out all commands having a gap in it, okay? So you can see it's just very much, okay? So then you just study each of them to see. So of course this is not you want. These are plot functions. So you will see that, oh, there's a gap, Minicons gap metric. Okay, so it's called gap metric. There's a command. There's also a command to do the gap in here. Also a command to new gap in here. Okay, so you use keyword to look for what you want. But sometimes you really want to know, this gap is in which toolbox, which direction. So there's a command is called which. So see, I have a gap metric in here. I want to understand this command is in which direction. So obviously it is in a robust toolbox and gap metric. Okay. But you also can find out what's the gap. Okay. Oh, gap is old. Can you see? Our robust control toolbox obsolete. Okay, there was a new toolbox and then there's a gap defined. So in other words, you should not use gap anymore, right? You should use gap metric command. Okay, you should use this guy instead of this guy, because they say, yeah, robust is an obsolete tool. So someday it will just maybe purged serial way. So I'm pretty sure mu is also mu gap. Mu gap. Oh, sorry, new gap. Sorry, nu. Is also in obsolete. Okay. So these two are what I learned. Okay. It's not necessarily have to. It can be just combine them together. So that's you find out using. I told you look for which. Okay. So then you want to know what is a gap metric. Computing the gap and the Minicons gap metric. Okay. Minicons gap. So this is still relatively new. Okay, gap metric, a new gap metric, and people are not very familiar with like left normalized coperion factors, right normalized coperion factors, normalized coperion factor model reduction. Okay, you just can read. Okay, and how to do a normalized coperion factor margins. What's the perturbation, how big the margin can tolerate, and so on and so forth. Okay. So you'll return a metric gap and new gap simultaneously, and they have a tolerance like 10 to the power minus 3 as default. So then the value should be between 0 to 1. 0 to 1. This shows the distance between two planets. Okay, two planets. When it is small, that means they are close. When it is close to 1, that means they are very different, extremely different. Okay.
It's normalized?
Oh, everything is normalized. In fact, they cannot be greater than 1, according to their definition. So I think okay if we just do that without knowing the equations, but I think it's time to see what is a gap metric. Wait a minute. Okay, so before we do that, there's something called WNO. This is the hardest part. I have to be honest, I'm not 100% sure I 100% know it. Okay? Okay. So it's called winding number. Winding number. Okay? So you have learned Nyquist theorem, have you? So you say you have a S plus 1. What is a Nyquist plot? For S is 0 is 1, right? And for S is infinity, you will come to here, 0. So you come on something like this, right? This is a Nyquist plot. Can you see it? But if you say, I got a square here, so what are you going to get? Okay? You get something like this, right? If I do third, okay? So what I'm going to get is also from here, but I'm going to do here, right? I'm going to do here. Right? So then if I keep going, so I'm going to have how many? Okay, keep going, right? Keep going. But if I have a very big K here, okay, so of course it will stretch me to here, right? So it is possible that I'm going to encircle. So there's a concept is called encircle. Okay, encircle is 1.-1, encircle -1 J0, -1 J0 point. Okay, if you encircle that, then you put this thing as a closed loop. Then the system will be for sure unstable. That's discovered by Nyquist. So you simply plot this is called next part, is a real part, imaginary part, okay? Imaginary part. So then I just see whether you encircle, okay? My minus 1J0 point. If you encircle, then you will be in trouble. But however, it does not mean he actually discovered this is for regular open loop stable system and rational, proper. But what if I have some scenario like this? So I have a -1 here, okay? -1J0 point here. And I have something here, okay? I start from here, I encircle it, okay? So I could encircle multiple times, right? I could encircle it multiple times. Or I could encircle it and then come out. Or even I have some other ideas, like you have encircle and somehow you do a counter clockwise and clockwise, okay? So that kind of thing you need to count. You encircle how many times, and then you go this way, encircle how many times, okay? So then the total net encircle number is called the winding number, okay? Winding number, WMO. So this part, don't worry, okay? Winding number, don't worry. And this type of thing, this is a singularity point. It's called next point. Okay, next point. Okay, next point. Let's go to this picture. So, why we need to introduce the winding number? Okay. Otherwise, you cannot tell very well. So, without winding number, it will be useless using this metric, okay? So, assuming that you perturb the system, otherwise this is 1, okay? Otherwise this is 1. So P2 and P1 are the same, okay? If this is 0, they are the same. But you do have a asymptotic cancellation of this unstable modes in here. So we know that P2 is increasingly difficult to stabilize as epsilon goes to 0. You have an unstable pole-0 cancellation. Remember our inverted pendulum in the card? So that epsilon is related to your relative length and mass. Okay? So it's very interesting that even epsilon is very small, you have a controller that can stabilize this one, closed loop, you stabilize it, okay? Will definitely destabilize the system for sure, okay? So you can see one of this margin is 1 is very small, epsilon is greater than 2. And in this case, it is interesting to see what is the gap metric. So in this case, gap metric and the mu gap metric are the same. It's 1, meaning it's extremely different. Extremely different, okay? Extremely different. So again, if we use H infinity indicator, I will introduce the phi next, okay? That is also a metric, and measuring the distance between them, and the infinite norm is very small. And that fails to indicate the difficulty of the problem. So in other words, gap metric is important, okay? Gap metric is important. So remember, remember, this is 1. This is 1. Why this is 1? Okay, why this is 1? Okay, we are going to see the real definition of the mu. Remember, when we define the G, we haven't talked about winding number at all. We don't need a winding number. Okay? Just P1, P2, I give you, So I give you a taste that you have 2 systems we are going to study. Who is the real metric for us to use? There's a definition, okay? But to do the definition, we need to talk about winding numbers, okay? This is the hardest part. I want to skip this part, okay? I want to show you the definition. So this winding number is very lengthy, okay? Very lengthy. So let's go to, we'll come back to the winding number when time allows. So remember, I have a phi. What is a phi? Phi, P2, P1, and remember this is a left and a right, known as covariant factors, okay? But the cross product of them together, so phi is this, and theta is that, okay? Like that. So I believe this is similar to, so you can see you have a N2 here, you have N2 tilt, N2 tilt, but this is totally different when you add tilt here and there, so you understand, okay? So these are the 2 definitions. So this delta phi, okay, if we do P1 and P2, we do a minus, okay, what are we going to have? So I think it's probably not hard to do here. So P1 is M1, okay? Let's do an M1, okay? And P2 is, they do the same thing to me. We don't distinguish. One is left, one is right, okay? But in Seiso case, it's the same. They say N2, M2, okay? M2. Okay. So I do P1 minus P2. I'm going to have M1, M2. We have N1, M2 plus M1, M2. Let me see, we will have this plus sign here. N2, M1, yes. N2, M1. Probably not this way. Okay. I'll put a question mark in here. So probably it's not this way. We need to check Minicons textbook for details of the derivation, why phi and theta is defined this way. Okay, let's accept that. Then you have denominator theta is not 0 for all omega. And also this winding number of this, okay, is 0. Okay, it's 0. Then it's okay. You use this definition as the new gamma metric. Otherwise, okay, if you have a winding number is not 0, then it is 1. It is 1. Okay. So, the new gamma metric is symmetric. So if you swap P1, P2, they are the same. Even doing the transpose, they are the same. Okay. So the tolerance is there, and so in this case you have 1 and integrator, okay? So then you have M1, N1 is the same, then multiply M1, N1, multiply will be 1, right? Add together, okay? And M2, N2, so you also have not necessarily strictly proper, just proper RH infinity. So RH infinity, so you divide it, you will have N2 divided by M2, you have that. So according to the theta and phi definition, you have this one, you have this one. So then you do H infinity norm of this one, you will get this, okay? And the winding number of the theta S, there's no poles, no zeros, this is a constant. Okay, so you don't have a winding number. One number is 0. Okay? You don't cross that. Okay? So there are some other ways to detailize, to simplify the winding numbers. It's a whole book. I think we need to. So there are other ways to define the new gap metric. Okay? And there's also look at those equations. I think we have seen this example from the beginning, okay? From the beginning. So can we say that P1, P2, P3, which one is closer to which? So we can do the mu gap metric. And it's interesting that the winding numbers, they will take care of the winding numbers, in fact, okay? Inside the commands, you just can tell it. So P1, P2, new gap metric P1, P3. So they are, so the gap metric is the same because the winding numbers are 0. Okay, so you don't have a difference. I think when you have a 0 in the right half plane, your winding numbers will be very different. Okay. So you can see 1 and 2 are much similar. And P1, P2, so P3 is kind of quite far away from P1. So P1 and P2 are considered as a close, okay? And P2, P3 and P1, P3 are different, okay? So compared to that, you will see there's a relative degree difference as well, okay? So that probably is interesting. So if you can stabilize P1, P2, but P3 may not be able to get stabilized. Although others are the same, like gain is 100. So this is in a SISO case, by the way. But remember, we can extend in the MIMO case. In the MIMO case, you have no clue what's the distance. Okay. So, in other words, we are having a very powerful tool. Okay, new gap metric. And the robust control toolbox gives us the powerful tool to get these numbers, okay? Get numbers. So, okay, we still have the winding numbers not very solved. Can I leave this one for you to read Minicons' book? There's very detailed description of how to count those winding numbers, okay? I roughly showed you that you increase the relative degree, your winding is different, okay? Winding is different. And if you have a 0 on the right half plane, then the winding is very strange, okay? It's very strange. So let me give you another example here. I have seen this before. So let's say I have one of S, sorry, this one. Yeah, one of S and one of S, or 1 plus S. Okay. So when S is 0 is 0, is 1, right? When S is infinity is minus 1, right? Okay? So the omega is 0 is here. Omega is infinity is here, right? When omega is 0 is here. Okay? So let's say when omega is 1, so you have 1 minus j1 and 1 plus j1. Okay? And then what do we have? The magnitude is 1, right? The phase is not. Magnitude 1, the phase is minus 90, okay? So this is minus 45, then this is a positive 45, so it's minus 45. So this is omega is 1, okay? Omega is 1. So then we're going to have something here, okay? Right? But what if I have 2 here, so then you have minus 2, right? This is also 2. Okay, so if I have 2 in here, so I should go 2 here. Okay. So it is a minus 2. Okay, minus 2. So you end up in here, Okay. So of course, if you do this is 2 times. Okay, if you do n, so let's square. So you are going to have something very different, right? So you end up with minus. So here is y is minus 180. Okay. So you have very different encircling pattern in that way. Okay. Very different. So what if I have different poles, different zeros on the right-hand plane? Very different. So what I'm saying that suppose you understand the new gap metric, okay? If you don't have a winding number, so this gap metric and the new gap metric are the same, okay? Are the same. But in general sense, new gap metric is more precise. So 2 more slides we can finish here, okay? So it is called extended loop shaving design. Extended loop shaving design. So basically, I assume that you have a nominal plan, P0 in here, as a nominal design. So we'll find a controller have a largest possible robust margin in terms of BPK, okay, BPK. And so if you design not on the P0 but based on the P1, another person from the P, okay, from another member. So then you know that for this P1 you have this inequality. This is what I said, beautiful part, okay? So you know you have nominal system, then anything else will be greater than this one minus this, okay? So I want to find out what's the smallest possible for all the members inside the family P, and we assume we set a lower bound, okay? Lower bound. So then for the lower bound, we simply know that for the new one here, the lower bound is here, and you need to tune your controller to satisfy that. So in this way, it's an iterative optimization process, okay? So it becomes, you design a weighting filter such that the magnitude is limited by that. Okay, and in the end, you can still find a controller K using this weight. So there's a procedure designed for that. So it's similar to loop shaping, but the spirit is from using the new gap metric. Okay, it's new gap metric. This looks similar. Okay, to our Glove McFarlane scheme. The difference is to find out WS. Okay, WS, and such that this is minimized. You find a infinity control. Okay. Then if the beta is very close to 1, fine, it's done. But if it's too small, then you can increase the alpha and start to iterate. Okay, iterate. So if the beta is too small or too big, you decrease the alpha. Okay. So let me show you what is the alpha. Alpha is defined in here. This one here, okay. This one here. So you search all the family of P, then so you have a lower bound alpha. But you do not know what is the alpha, so you have to search it, so iterate it. But when to stop, you need to introduce that kind of beta, okay, index. Beta around 1 is considered as good design, done, okay? Okay, so gap metric, I know it's a little bit difficult. That's why we used 2 lectures to cover 1 whole book, okay? And I want to, later on, I want to show you that, actually I have them here. So this one. People ask a question, oh, is a new gap metric used for industry applications? Okay. But unfortunately, the answer is not very positive from this guy's work. But there are some people using a lower order Boston new gap metric, the kind of design, similar. But before I let you go, I want you to see something here. Okay. So if I put a gap metric, it's only 230 papers. Okay. So that's amazing. Amazing. I didn't know that. So then I just did the newest first. Oh yeah, there are people in 1918 still following that. So I want to show you one paper that you should pay attention. Say for example, this paper. Time domain data-driven approach for the estimation of closed loop stability margin. People are using non-normalized covariant factorizations. And yeah, they're also introducing a new measure for dynamic similarity of nonlinear systems based on gap metric and deterministic learning. And look at this one. This is the most interesting one to hire. Scheme for fault detection using a data-driven gap metric technique. Okay, okay, you know, this is funny. Yeah, so it's 2018, not too old. So if you want to do cutting-edge research, please dive into gap metric. Probably will make your work more publishable, I think. Okay? Because many other people do not use it. Okay, we're stopping here. Hey, today I hope you will go to our lab in the new building, not go to that lab, okay? Lab in the SRE building, okay? Also, we can do the sitting area outside of my office, so we can talk. So, 2 o'clock meeting. After that, since 3 o'clock,
maybe 3:30. I'll be available until 5 or 6, 5:30.